我是陶静，我是中国科学技术大学物理学院的陶静。我们今天下午很高兴请到了这个来自就是美国Nebraska 大学 Lincoln 分校，当然这是它的主校区物理学院的这个物理系物理和天文系的洪霞教授。那么洪霞教授呢，他的本科是在北大拿的，然后接下来他在耶鲁获得了博士学位。在 Penn State 做完 postdoc 以后呢，那么他就加入了这个就是 University of Nebraska at Lincoln，从 assistant professor，那么现在已经是一个 full professor 了。洪霞教授呢，他在就是做 assistant professor 期间呢，陆续拿到了这个美国 NSF 和美国能源部 DOE 的这个杰出青年科学家奖。我就是非常高兴，是因为我认识洪霞教授也有些年头了。当然一开始的时候呢，虽然知道他，但并不熟。后来我们共同在能源部的这个就关于 electron probe 这样的一个这个 program 里边，就是我们都被那样的一个 program 所支持，所以对彼此的研究有了更多的了解，而且这也促进了我们的一些合作啊，并且我们还分享过一些我从他那里就是有交换学生，我们就共同感兴趣的科研问题呢，有过不少的讨论。我对洪霞教授印象最深的一点就是他经常就是他的物理功底非常好，他经常会就是在听别人报告的时候呢，他会问一些很聪明和尖锐的问题，所以我今天就是感觉很庆幸的是。幸亏是他在给报告，而我坐在下面听。好的，那么我也不用多说废话了。那么，洪霞教授，如果你准备好了，那么可以开始给报告了。
好，谢谢啊，就是非常感谢陶静的邀请。然后我现在也是比较的懵，就是这个形式我以前没有给过。然后呢，我会接下来用英文来介绍一下我们组最近的工作。Good afternoon. So it's my great pleasure to share with you our recent progress in studying ferroelectric van der Waals heterostructures, where we observe a range of interesting electronic and optical phenomena. So I'd like to start with a brief introduction to ferroelectrics. If you plot the free energy as a function of a displacement field, for a normal dielectric material, you expect a parabolic relation. But the ferroelectrics show a double well energy that settles at a non-zero spontaneous polarization. This polarization can be switched between different orientations by applying an external electric field above a critical value. We call it a coercive field. Since its initial discovery in 1920, it's already over 100 years, ferroelectrics have been applied for many device applications. Here, I just give a couple of examples. For example, the nonvolatile polarization can be used to define the on and off state in a nonvolatile memory. Both bulk and domain wall of ferroelectrics exhibit a photovoltaic effect, which can be used to construct solar cells. And ferroelectric materials also show ferroelectricity and piezoelectricity, meaning the polarization changes as a function of temperature and mechanical stress. So they're used for thermoelectric device and mechanical energy harvester. There are recent research interests focusing on the negative curvature in this free energy profile. So basically, it can be modeled as a negative capacitance, and it can be adopted to build low power logic devices. Here are at least 3 classes of, let me see if I can make a laser pointer work. At least 3 classes of most used ferroelectric materials. The ferroelectric oxides, such as perovskite, lead titanate, are known for large polarization and high Curie temperature. The polarization originates from the displaced B-side cation ion with respect to the surrounding oxygen octahedral. For ferroelectric polymers such as PVDF, they have the advantage of being flexible and transparent. Recently, there are more interest on the van der Waals ferroelectric materials such as copper, indium, phosphorus sulfide. So this material has highly mobile copper ions that is displaced with respect to the sulfur cage that gives the polarization. and it gives this very unusual negative piezoelectricity and quadrupole well. Because those materials can be mechanically exfoliated to nanoscale, it's a model system to study the finite size effect for ferroelectricity, and it can be stacked with other wonderful materials to form multifunctional devices. Important property for ferroelectrics is the domain formation. As the surface of ferroelectrics has a high density of charge, it's actually energetically favorable to break into smaller regions with polarization pointing to different direction. The boundary between two of these regions is known as a domain wall. It's a topological defect that shows unusual conduction. For the domain wall in bulk, it's icing type, so it can be extremely narrow, just a couple of unit cell, but towards the surface, neo-type domain wall has been observed. It has also been shown that you can engineer in depolarization field in the system, forming this kind of flux closure type domain wall that can show negative capacitance mode. So if you work with the ferroelectric thin films, you can basically achieve nanoscale domain control using conductive AFM. You can also image this domain structures and domain wall using either piezo response force microscopy or second harmonic generation. Those are the techniques we use. So what we're interested actually is in interface of ferroelectric material with a 2D dimensional channel and observe what kind of a interface synergy that can be induced. If I put two different classes of materials next to each other, there are different interfacial coupling mechanisms. Just to name a few, the interface coupling can be mediated by charge, such as in a field effect device. It can be mediated by lattice, such as in epitaxial growth. It can also be mediated by polar symmetry that generates nonlinear optical response. So today, I will basically give examples for each of these three scenarios. I will first discuss how we combine ferroelectric field effect with the nanoscale domain patterning to create a programmable junction states in 2D semiconductor moly disulfide. We also explore the joint transport anisotropy in rhenium disulfide. Then I will show you how the epitaxial coupling between the ferroelectric polymer and the rhenium disulfide can lead to formation of large scale ferroelectric nanowires, and how we can actually achieve tuning of nonlinear optical signal at the moly disulfide PZT interface. So I will first discuss the ferroelectric field effect. This project is led by my former postdoc, Dawei Li, Jinfeng Song, and graduate student Zhiyong Xiao. Moly disulfide is a layer 2D semiconductor. In the monolayer limit, it has a direct band gap of 1.8 eV. If you fabricate into a field effective structure using a dielectric gate, such as hafnium oxide or silicon dioxide, you can basically use gate voltage to tune the Fermi level and change the channel current. Previously, a switching current ratio of 10 to 10 has been achieved. What we want to do is replace the dielectric with a ferroelectric gate. So here, the nonvolatile polarization can either attract electrons in the system, basically raise the Fermi level close to the conduction band and increase the channel current, or if I flip it, it can deplete electrons from the channel, lower the the Fermi level further into the gap and reducing the channel conductivity. So this will give me a non-volatile switching hysteresis. So let me just illustrate the effect using a MOS2 double gated structure. So it's a sandwich between a silicon dioxide backgate and a polymer PVDF top gate. Without a poling, polymer is in the polymorphous state, meaning polarization are all randomly distributed, and you can tune the channel current using the backgate. So now what I want to do is actually fully polarize the polarization using conductive AFM. Here shows a PFM image. You see I have a uniformly polarized polarization down state. It increases the channel current If I switch the polarization to the uniformly polarized up state, it suppresses the channel conductivity. So this process is non-volatile and fully reversible. We can switch it back and forth by tuning the domain structure. And because this is an electrostatic doping approach, we do not affect the channel quality. Here we model the band mobility of the channel for the P-up, P-down state. You can see the density dependence fully agree with each other, showing that in the polarization switching process, we actually preserve the sample quality. One thing we note is actually the on-off ratio of this approach is actually moderate. It's only up to 450 approach, a factor of 450. This is because the sample is polymorphous. The polarization are mostly random distributed, and it's very hard to align them. Later, I will show you how we can use a different strategy to enhance this effect. So now we have this ferroelectrics that's capable of modulating the sample between the metallic state and insulating state. So what we're interested in is actually create a junction in the channel. If we can have a system in the half metallic and half semiconductor state, then I have a homo junction that is a Schottky barrier. So we start with the sample. If you tune it in the uniformly polarized down and up state, you can see that we can change the channel LV curve by a factor of 2 orders of magnitude. But interestingly, for both states, what you observe is a linear LV, meaning I have an ohmic conduction in this channel. So now what I do is polarize the sample into a P-up, half P-up and half P-down state. And if I park at a minus 10 volt backgate voltage, in the P-down state, the sample already starts to turn on, and in the P-up state, is deeply in the gap. And we indeed observe a nonlinearity emerging in the IV characteristic that can be well described by the Schottky barrier behavior. So to further understand it, we basically map out the channel IV characteristic as a function of the source drain voltage and the gate voltage. Superimpose on it are the IV transfer curve showing here for the uniformly polarized state. So you can see that the IV characteristic can be divided into 3 regions. In region 1, for both channel, we have it deep in the gap, so it's highly insulating, but it's a linear behavior. In region 3, for both channel, it is basically conductive, and we see high conductance, but it's also a linear behavior. It's only in region 2, when the system is half in the gap and half in the conducting band, we see this very nice Schottky barrier behavior. We can further heat up the sample above the melting temperature to remove the domain structure, and you can see that it comes back to the original IV, showing the process is indeed fully reversible, does not hurt the sample quality, and the junction state is indeed due to the domain writing. When we tune the backgate, as we are tuning the voltage of both the both sides of the channel, so basically we can actually modulate the Schottky barrier. So we use a semi-harmonic emission model to model the IV and extract the effective Schottky barrier height, and show that in a single sample we can actually tune the Schottky barrier from 350 to 550 millivolt. What I just discussed is the creation of a homo junction. We can also create a heterojunction if we just write domains on the contact area to change the contact potential. So here we have monolayer moly disulfide sample, and keeping the contact polarization state the same, but only tune the electrode area, the domain structure. You can see that we have observed the linear LV, but having the channel conduction changed by a factor of 100. If we actually create asymmetric domain writing, so if I just write one in the P-down state, the other one in the P-up state, instead of linear LV, I have this highly nonlinear rectified IV, and I can actually reverse the rectifying IV direction by reverse the domain writing. So this approach has also been adopted by other groups to write, for example, PN junctions in monoditelluride and you can observe clearly photovoltaic effect in those devices. So now I want to change gear and apply this approach to explore the intrinsic transfer anomaly in another material, disulfide. So this material has attracted lots of research interest because it can be a direct bandgap semiconductor even in the field layer. And previously, its anisotropic in-plane structure actually is reflected in the highly anisotropic optical measurements. The question is, how would this structural anisotropy would affect the transport properties, which is relatively unknown. There's one study showing that we can actually fabricate an array of point contacts around a disk sample and measure the conductivity along each pair of the electrodes. And they find that the anisotropy ratio between different orientation of the sample is a factor of 3. So this is a red data points. And this is much smaller than the theoretical prediction, the blue data point. And you can see the angular dependence also do not match well. This is because in this device configuration, the current path is not well defined. You can see that for each measurement, we're actually collecting current that are going through different directions. So basically that will attenuate the overall anisotropy when we're sampling the current along different directions. To address this issue, we actually propose a different device structure. So here what we want to do is start with a single channel and put using the ferroelectric top layer to put the entire channel into the insulating state, right? A very narrow wire, so along electron only flow along this direction. So by actually write different nanowires with different orientations, we can map out the directional transport. So the only challenge of this approach is we need a state that we can actually put the entire channel into the insulating state. But working with polymorphous PVDF, this looks unlikely. Here I show the transfer curves measured on a bilayer rhenium disulfide sample, and you can see that by switching the polarization of this polymorphous PVDF top gate, we can only change the sample by a factor 100 times in the current. So we cannot really turn the channel off. So we subject the sample to a very gentle thermal annealing at 135 Celsius to improve the crystallinity of the sample. And surprisingly, the effect is drastically improved. Here you can see that after thermal annealing, we can have a giant change of the channel conduction. We observe the on-off ratio up to 1.4 times 10 to 8. Note even a larger effect is expected when the gate voltage is between 15 volt and 30 volt, but the current of the offstate is too low that we cannot measure. And above 30 volt, we can actually change the channel from electron doped to hole doped. So this means we can write a PN junction in this device. So now we have this improved field effect. We're going to define the entire channel into the insulating state and write domain nanowires domains in different directions, and measure the resulting conduction. So you can see that we work with exactly the same channel by simply varying the nanowire direction. The transfer curve changes drastically. If we have the nanowire writing close to the B-axis, so this is the B-axis, for the 30-degree data and 150-degree data, we see the channel is highly conductive and electron doped. If we have nanowires that is perpendicular to B-axis 90-degree or close to it, for the 75-degree, the channel is highly insulating, and then we see a change from N-type to P-type behavior. So that means at this sample, we can actually achieve a conductivity variation over a factor of 55,000 on the same channel. So using this approach, we have tried to map out the transport anisotropy in monolayer, bilayer, and 4-layer radiant disulfide samples. So here is a polar plot of the conductivity. And there are a couple of common features. So for all those samples, it's most conductive along the B-axis. This is a radiant chain. And the least conductive along the direction perpendicular to B-axis. Also, if you look at the data, they don't have a mirror symmetry around 0 degree. This is because the low symmetry of this device actually it doesn't have mirror plane. The only symmetry it has is inversion symmetry. Another interesting observation is actually when we increase the layer number, the sample becomes more anisotropic. So this is high. We observe a much higher anisotropy in the 4-layer radiant disulfide sample. So to understand the origin, we performed the DFT calculation of the electron band structure of those samples. So here you can see the dispersion relation along the radiant chain. So this is around the B-axis, the kx direction, and perpendicular to it is ky direction. Immediately, you can see the transport anisotropy is related to the change of the electron band structure, as we have a much heavier effective mass along the ky direction, which can suppress the mobility of the sample. So here we plotted the calculated angular dependence of the effective mass, 1 over effective mass, and overlay the experimental data. For monolayer data, basically we can have a good agreement between theory and experiments by considering both the effective mass and the anisotropic electron phonon interaction. For the bilayer and the 4-layer, the anisotropy of the band actually increases, and you can see that the band anisotropy alone can account for the variation of conductivity. We also find that the anisotropy indeed increases with the increase in linear number, and actually for the 4-layer device, there's an emergence of a flat band. So this will be a very interesting system if we can look into collective behavior such as magnetism or superconductivity at the reduced dimension. So having discussed the charge-induced effects, next I want to focus on lattice-induced interface interaction. So I will show you how the interfacial-epitaxy relation between a ferroelectric polymer and the radiant disulfide can lead to scalable formation of a large-scale crystalline nanowires for PVDF. So this work is led by my postdoc, Li, and graduate student, Kun Wang. So as just mentioned, we put the PVDF under a very gentle annealing at 135 Celsius and see a drastic improvement of field effect. So why? To understand it, we performed in situ FM imaging of the sample. So what's shown here is we actually progressively increase the sample. The sample start with a structureless surface that is very smooth. But when the sample is heated at 120 Celsius, you actually can see that it becomes very textured. And we see small segment of texture that is either along the vertical or horizontal direction. And when we further heat it to 130 degree, actually we see there are well-ordered, close-packed nanowires that is forming. And when we cool down the sample, this nanowire structure is still stable. Similarly, we'll put the PVDF on silicon dioxide. And when we heat it up, because the melting temperature is around 100 Celsius, we do not see any nanowire. Instead, we see some droplet structure forming. That is, when we cool down, it's still in the droplet. It doesn't go back to the wire state. So clearly, radiant disulfide base layer is very different from silicon dioxide. So we want to know what is the driving mechanism for this nanowire formation. So we actually prepared the PVDF sample on different wonderful materials. For the isotropic base layer, graphene and molybdenum, what we see is after annealing, indeed there are short segments of nanowires forming, but because the substrate is isotropic, a nanowire also is randomly oriented. This is a result on graphene is also previously observed. So maybe it's an isotropic structure of the wonderful material that drives this directional growth of nanowires. So we also tried black phosphorus. Surprisingly, no, we still see this kind of rice structure that are randomly oriented, and we see larger voids. Only on rhenium disulfide, we see highly ordered PVDF nanowires that are well aligned and close packed. To understand the direction and the length scale of this interaction, we actually prepared two rhenium disulfide samples and having their B-axis actually perpendicular to each other. So this is identified by polarized Raman experiment. So here shows the FM morphology of the small region inside this green box. You can see that for the region that has only one layer of rhenium disulfide, we see that the orientation of nanowire is always perpendicular to the B-axis of rhenium disulfide. And this orientation would actually slightly extend to silicon dioxide, and they compete with each other, forming bundles. And eventually, when it's far away from rhenium disulfide, it becomes randomly oriented as on silicon dioxide. However, for the overlapped region, you can see that the nanowire orientation is only determined by the top nanowire. So there's a continuation of the forming, and it ends sharply at the boundary with the bottom rhenium disulfide. So we thus conclude that the interaction is extremely short range. It is only affected by the crystalline orientation of the interface layer of rhenium disulfide. This approach is highly scalable. What's shown here is a sample actually close to 1 centimeter size, and we have formed this large-scale nanowires, nanowire films on the whole surface of this sample. So since this interaction only occurs at the interface, we have a hypothesis that it's probably driven by the structural change. So we did a TEM. So from the cross-sectional TEM image, we see that the nanowires are indeed close packed, and they're interesting. They are single crystalline. Okay, so if you take a closer look at the interface, we see that actually the PVDF nanowire forms an epitaxial relation with the rhenium disulfide. So they are actually lattice matched. And because of this lattice match, we actually have the polarization of the polar axis of PVDF actually is forming perpendicular to the sample plane. This is very unusual because for most of polycrystalline samples, it prefers a 30-degree alignment. That means the polarization of this P nanowire would be actually much higher. So this is further confirmed by the PFM measurement. What we have done is basically first perform the vertical PFM, and we can switch the polarization, and then we perform the lateral PFM to see if we have in-plane component of polarization. And we find that when we change the imaging angle, the lateral PFM signal is always at the noise level. So it confirms that indeed we have actually a polarization of P nanowire fully aligned along surface normal. So to understand it, we actually consider what actually drives the morphology of PVDF. So there are mostly two energies in place. One is a surface elastic energy that want to increase surface to bulk ratio. So it prefers to spread out, forming thin films. But because the wonderful surface is hydrophobic, so it actually has a repulsive interaction, and you want to form a coerced surface so that reduce the interaction surface. And now we have the third energy that is in play, which is the epitaxial energy, which can also reduce energy. So now we would understand why we actually form a nanowire, because the nanowire is always spread along the direction when we have a very high density of bonding between PVDF and rhenium disulfide, so that the epitaxial energy helps to reduce energy and prefers to spread the material. But in the perpendicular direction, we actually have less bonding between these two materials. That means that I don't have enough energy gain by forming spread the material, so it will want to actually curve it up, forming a nanowire. This is actually a self-terminated process. We have changed the amount of starting materials from 1 monolayer PVDF to 9 monolayer. We find out the width of the PVDF nanowire is always 35 nanometer, showing that it's really the energy competition between these different energy scales that determine what is optimal size of the nanowire. What is more interesting is when you don't have enough material to spread over to cover the entire surface, you actually see some voids. But if you take a closer look inside, you find no, they're not empty. So we still have PVDF inside, and it actually forms a smaller nanowires. For those smaller nanowires, the width is around 10 nanometer, and you can see that they actually have extremely small coercive field. So it's about 0.1 volt. Can be 100 times smaller than bulk PVDF materials. So this is good for low power applications. To understand how the nanowire formation would affect the field effect experiments, what we have done here is basically perform an in situ measurement. When we heat up the sample, we actually measure how the conductivity change. And we find that when at 120 degrees, this texture structure nanowires start to emerge. There's a jump of the doping into rhenium disulfide. This suggests the sample PVDF starts to crystallize. And at 130, the nanowire forms, and we can see that the doping become maximized. For the thinner nanowires, is slightly different. We can see that the texture structure happens actually as early as 60 degrees C, and the field effect is much larger, so showing that the monolayer PVDF nanowire actually has a much higher crystallinity. So we basically can conclude that we have a two-stage process for forming the nanowire. So we start with the polymorphous material. We have the amorphous parts, the polycrystalline parts. And in stage one, when there's enough thermal energy, basically they would actually form short segments and start to actually rotate and merge. And in stage two, they would form merge into larger wires. It's either 35 nanometer width, or if you don't have enough starting material, 10 nanometer width nanowires. So for the last part, it's talking about the polar symmetry. Actually, it gives us a very interesting optical effect. So in previous studies of ferroelectric van der Waals heterostructures, most people have been focusing on field effect. For example, here people have been writing domain structures and observed that the photoluminescence intensity has been modulated. And this has been attributed to the doping change. On the other hand, one thing that was not well studied is the polar part, because the monodisulfide actually is also polar, and it has been shown that it can have joint in-plane piezoelectricity, and you can also achieve ferroelectric switching in this material. So the question is, if we actually combine the monodisulfide with the ferroelectric oxide, such as PZT, what we can observe. So we carried out second harmonic generation this technique is highly sensitive to symmetry breaking. So we have incident laser in, and we see the trying to detect the photons that has a double the energy in the reflected mode. The initial thought is we should not see anything, because if I put myself in the instant light point of view, indeed there's a breaking inversion symmetry for for the molybdenum. But for PCT, because the polar axis actually is along the propagation direction of the light, we do not expect any symmetry breaking. So is that the case? So let's just look at what will happen in ferroelectrics if I have a domain wall. So previous TM study has shown that the domain flipping actually is not icing type when you are close to the sample surface. So you do not have immediate transition from a polarization upstate to a polarization downstate. Instead, you can actually have a flux closure type rotation of the local dipoles, forming something like a new type wall. And now if you have a normal incidence of light, you would see actually in-plane symmetry, inversion symmetry is broken. So we actually prepared a 50 nanometer epitaxial PCT thin films, write polarization up and down domains, and try to measure the second harmonic generation signal. Indeed, so for the uniformly polarized domains, we do not see any nonlinear optical signal because there's no in-plane symmetry broken. But we see strong SHG signal at the domain wall. In fact, if you apply an analyzer, you find the light is already polarized. For example, here we apply a perpendicular analyzer, we see that only the horizontal domain wall. If we apply a horizontal analyzer, we see this is a vertical domain wall. So the polarization of the light is always perpendicular to the domain wall orientation. So that makes sense because this is basically following the chiral rotation of the dipoles at the domain wall surface. So now what we did is we overlay a monolayer MOS2 on top. So here, this is the domain return area. And immediately you can see that MOS2 have strong SHG signal, but the SHG signal close to the domain region is actually modulated. We also characterize the photoluminescence, and indeed we see the modulation of the photoluminescence signal associated with the doping effect. So now let's take a closer look of what the PCT domain wall would do to the second harmonic generation signal on MOS2. So this is what I just showed with bare PCT. Now I have the MOS2 laid on top of it. And you can see that without applying an analyzer, I'm going to see both horizontal wall and vertical wall on bare PCT. But when MOS2 flake is on top, the vertical wall does not show any contrast. Instead, we actually see horizontal wall similar to as if we have an analyzer applied. So in other words, MOS2 serves as a top level analyzer to pick up the SHG signal. And this analyzer actually has also a non-uniform tuning effect. We basically see enhanced, suppressed, alternating modulation of the SHG signal. And again, the light is fully polarized and it's perpendicular to the domain orientation. So this actually can be understood by this chiral rotation of domain local dipoles at the domain wall. So you can see that for the region where we have the enhanced HG signal, we always have a dipole that is flowing from up to down. So this is up to down. So that means we have the polarization at the domain wall that is aligned with the polarization, in-plane polarization of molybdenum. But for the region where the SHG signal is suppressed, we always have the rotation from down to up. down to up. So here the chiral rotation of the local dipoles would create an in-plane polarization that is anti-aligned with MOS2. So we use electromagnetic theory to model the second order tensor for the SHG signal, and we find that this will explain the enhancement and the suppression. And surprisingly, this suppression of SHG signal is very, very effective. So what's shown here is a crack. So it exposes the bare PZT, and you can see that we expect there's no SHG signal. And here, the tuning of SHG signal by the domain will actually match this. So this is a very effective cancellation. So assume that the domain wall can generate a similar amplitude of SHG signal as the MOS2, and model the effect. What's shown here, basically we have a same flake of monolayer MOS2 put on domains written in different orientations, and this is the electromagnetic theory modeling, and you can see the amplitude modulation can be well explained by this scenario. So microscopically, why is the case? To understand it, we performed DFT calculation of the dipole in-plane polarization for PZT and for MOS2. And this is just a very nice coincidence that you can see the in-plane polarization of MOS2 actually match very well with that of the in-plane polarization of ferroelectric domain wall. So that is why we can have such effective tuning of the HGHG signal, because the dipole can mostly cancel each other or boost double the effect. So what I have shown you is basically we can either working with a top gate such as a ferroelectric polymer, right domains, create junctions, or we can work with oxide backlayer that can give you this very nice SHG tuning. So the question is that possible we can combine these two effects? The answer is yes. So we have some recent progress in fabricating ferroelectric oxide membranes. So this is done by epitaxial growth of ferroelectric oxide on water-soluble buffer layer and etch the buffer layer away. And then we can lay the pick up the oxide membrane and stack it with van der Waals materials, similar as you would fabricate a van der Waals heterostructure. So here we show that by putting PZT membrane on top of MOS2, we can actually achieve the tuning of second harmonic generation. So this is done actually, we can rewrite this domain because this is we're working with a top layer of oxides. We have also put oxide as a top gate to gate a monodisulfide transistor device, and here it shows that by changing the polarization using conductivity AFM, we induce orders of magnitude change of the channel conduction. So this is basically 200,000 times of modulation of monodisulfide. So if in the future we want to continue the line of combining PZT membrane with the van der Waals heterostructure, which allows us to combine linear light filtering with programmable electronic states. For this work, I'd like to acknowledge my group members, and former postdocs and graduate students for the contribution. We also work with Steve Deschamps' group for PVDF, Yongfeng Lu's group for the nonlinear optical study, Jeff Shaw's group for TEM study, and Afghani Simbol's group for the DFT calculation. We have done the semiconductor device modeling with David Furry and domain or chiral rotation with Andrew Ripe group and polycrystalline ferroelectrics with Kino and Kim groups. this work is supported by US DOE, NSF, Nebraska-Lincoln, and EPSCO Equate Center. So this brings me to the end of this talk. What I have shown you is basically the ferroelectric Waals heterostructure is a fascinating system. As always, at the interface, you can always see something that is not available in bulk. And there are different coupling mechanisms. It can be coupled by charge, can be coupled by string, epitaxial growth, or it can be coupled by polar symmetry alone. And you can create a monojunction, programmable junctions, explore the intrinsic transport anomaly in 2D materials, and you can have optical filtering effect. If you can combine freestanding ferroelectric oxide membrane with bundle material, it also enables inferential programming of combined optical and electronic functionalities. So I think that's the end of the talk.